Okay, suppose your physics teacher has given you a problem and you're trying to visualize it, so you want to draw a diagram of the situation. Suppose I've got 3 dogs gnawing on a bone and I want to draw this. So we start with the bone, right? So we say, okay, so, helps if I'm on a pen. All right, so we draw a bone. All right. That looks like a bone, right? Cool. All right, I'm not much of an artist, which you will see very quickly if you haven't already figured this out. So now we need a dog. All right, dog number 1 is pulling on the bone straight this way with a force of, let's go with 80 newtons. All right, and then, boy, this dog, that is not much of a dog, is it? All right, so then our next dog is over here, and our next dog is pulling at an angle of 30 degrees this way. These dogs are happy. They're not well drawn, but at least they're happy. They're wagging their tails. All right, so we got a dog there pulling this way with a force of 70 newtons, and this angle here is 30 degrees with respect to the negative y-axis. And then we have a third dog over here, and this dog is pulling this way. That's a dog, honest. We're looking at it kind of from above. So we've got some ears, it's got a nose. All right, and it's pulling this way. This dog isn't very strong, pulling at 40 newtons at an angle of, let's call that 60 degrees. Okay, so there it is. There's our drawing, there's our diagram, and it's terrible. What is the problem here? The problem here is, there are many problems. One is that took way too long. All we want is to visualize a problem in order to help us figure out a physics problem, right? And it took way too long to do that. Another problem is that unless I already told you what this was, you might have a hard time figuring it out. I am not a good artist, and art and physics are not always things that people are good at, right? So that is to say, I'm not a good visual artist. I don't draw very well. There are some things I do well. Anyway, so this is a terrible thing. Nothing about this process was good, including the end product. It's basically just an embarrassing thing that I would like to get rid of as quickly as possible. So, in order to help a physicist or a physics student visualize and draw these types of problems, what we have is something called a free body diagram. And the free body diagram for this situation looks like this. Watch how fast this is to draw. Ready? Done. All right, so that is our free body diagram of our situation. It is easy to decipher. It is clear what it represents. There are 3 forces. We have the angles those forces are represented at. So what I want to do is I want to show you how to create these free body diagrams and then how to use them to solve problems, okay? So let's do that right now. There are 5 rules for drawing free body diagrams. The first is that the object should be represented by a dot at the center of mass. You can draw the object, a stick figure, a dog, a bone, whatever, but you then need to put a dot in the middle and then ignore the object you drew. The dot is the only thing that's important here. 2. Force vectors should all originate from the dot. Don't draw them near the dot. Don't draw them pushing on the dot. It doesn't matter if they're a push or a pull. The vector starts touching the dot and moves away from the dot. 3. Only force vectors and angles should be drawn on a free body diagram. Anything else, like vector components or accelerations, are unacceptable. 4. All of your vectors have to be labeled and they need arrowheads showing the direction. Again, that direction will be away from the dot. 5th, the exact scale is not necessary unless the problem specifies that it is, but some vague approximation is a good idea. Sometimes with an unknown vector where you don't know the force, you're not actually going to know. You might not know the magnitude or the direction of the vector you're supposed to draw. So if that's the case, go ahead and take your best guess. You will not have to go back and fix it later. All right, so here's an example that we're not going to solve the whole thing. We're just going to use the free body diagram to create some equations. So we have a cart that is being pulled at an angle to the right. The exact numbers here don't matter for what we're doing, but there is, you see that little mu there? There's some friction here as well. So I just want to draw this free body diagram first, following our rules. So rule number 1, right, is we start with a dot, yes? So we're going to take a dot and we're going to throw it right here. There's our dot. That represents our wagon, the center of the wagon. Next, we need to draw forces. This one is really obvious. There is a force here, F, at an angle theta. Those are things we're allowed to draw, right? There are other forces acting on this thing. There's friction. Friction always opposes motion, and this thing will be trying at least to accelerate to the right. So there is definitely a force of friction back this way, so we're going to label that force of friction. The other two forces on here that should be relatively obvious are that gravity is pulling it straight down. You can write Fg. You could also call this Mg if you wanted to. And then we have the normal force pointing upward. That's it. This right here is your free body diagram. If you wanted to do something else with it, you could draw it off to the side, but you'd leave this alone in nice, pristine condition and don't touch it from there, all right? Okay, so to solve problems with this, you actually just take each direction independently. In the x direction, take all the forces that are pointing at least partially to the right and add them up. The only thing pointing partially to the right is the force F, and it's only the x component of it. Take all of the forces that are pointing to the left. The only thing pointing to the left is the force of friction, not an x component, it's the whole thing. And then those have to add up to one of two things. If the cart is in equilibrium, then they will add up to 0 newtons, because that's the definition of equilibrium. All the forces have to cancel. If it's not in equilibrium, and in this case it isn't because we know there's some acceleration, if it's not in equilibrium, this has to equal ma. Fx is F cosine theta, so we get F cosine theta minus the force of friction equals ma would be our equation in this case. There's more details that go into finding the force of friction here, which we're not going to worry about for this particular example. All you do, once you have it drawn, is add up all the forces one way, subtract all the forces the other way, and then set it equal to either 0 or ma. In the y direction, everything pointing up, normal forces pointing up, and a little bit of force, the y component is pointing up. Pointing down is the force due to gravity. In the y direction, we know this thing is not moving, so this is going to be 0 newtons. It is in equilibrium in the y direction. So those are our two equations, one for the x direction, one for the y direction. That's how useful free body diagrams are, and that is what you're expected to be able to do with them. All right? See you next time.